Hello, everyone, and welcome to the first session of the QWave series. My name is David Morcuende. I'm the QuIC Network Manager, and I will be your host moderator for today's series. I'm just going to wait a little bit till I can see that on YouTube everything is going fine. Perfect. So, as I was saying, we're thrilled to kick off this series of webinar. This is the first one, so thank you all for being here. In this webinar series, we are going to bring together different leading experts in the industry, and maybe in the and all in the quantum landscape. So we are launching today with an exciting and relevant topic that is the journey towards fault-tolerant quantum computing in Europe. As you may know, fault-tolerant quantum computing is considered one of the ultimate goals in the quantum world, and achieving it, it could unlock a new era of computation that far surpasses anything that we have today. So during this session, we will explore how Alice and Bob and Riverlane are building these different technologies, and they will be showcasing their approaches. So I'm gonna introduce them. First, we have Earl Campbell, and I'm gonna jump him in. Hi, Earl. So he's the Vice President of Quantum Science at Riverlane. He's a world expert in quantum error correction, with nearly 2 decades of experience designing fault-tolerant quantum computing architectures. He holds a PhD from Oxford University and has contributed extensively to the field through his research and publications. He has been working with AWS and as a scientist, lecturer, and now he's working at Riverlane, focusing on building the quantum error correction star for quantum computing. And I'm going to introduce you our second speaker, Jeremy.
Hello.
So Jeremy is the chief of theory at Alice and Bob. He's an engineer. He also holds a PhD in quantum information science. He has been deeply involved in the development of the cat qubits that, if you don't know, he will showcase and talk about them for fault-tolerant quantum computing. He leads the theoretical research team at Alice and Bob, focusing on modeling those cat qubits and enhancing quantum computing architectures and developing applications tailored for their customers. So once we have both presented, I will let Earl to share their screen and their slides, and we can jump in. Remember that you can post questions on YouTube chat, and we will answer them at the very last.
Okay, so I share my screen now?
Sure.
Okay, thanks for the introduction. Yes, I'm Earl Campbell, VP of Quantum Science at Riverlane. So this presentation is going to be in 3 parts. So the first part I will present, and I will give you a general overview of quantum error correction and some of the really exciting kind of highlights of experimental demonstrations that have happened in the last couple of years as we really start to kind of enter the early fault-tolerant era. And so then I'll hand over to Jeremy, who will tell you something about Alice and Bob's approach to the problem. And then we'll finish off with a third part where I'll come back to me and I'll talk about Riverlane's approach to quantum error correction. But just to give you a bit of a spoiler, I've got this image on the right-hand side that I like to start off with that, that gives you a kind of impression of what Riverlane does, which is that we build dedicated classical electronics. We don't make qubits, we make classical electronics that helps enable our partners in universities or other companies around Europe implement quantum error correction in real time. And so we'll come back to what that image means later on. Let's just start off with summarizing what quantum error correction is. So quantum error correction is all about taking many noisy qubits and making them into a more reliable, what we call logical qubit. And so the idea is that today error rates of qubits are, say, 1% or 0.1%, and that's just not good enough to run algorithms that need, say, millions or even trillions of quantum operations. And so I like to introduce quantum error correction by talking about a specific code the so-called surface code, which is one of the most popular approaches. And so in this picture here, we've got a square kind of 2D array of qubits. Both the yellow and gray dots are representing qubits. The yellow dots are what I call data qubits. These are the ones that actually embody the quantum information, the logical qubit that we're trying to protect. And the gray ones are auxiliary helper qubits that help us measure these checks, which are shown in blue and red. So wherever I've got a blue square or half circle, it represents requiring that the qubits are in an eigenstate of, say, the XXXX operator on the data qubits at the corners of that blue shape. Similarly, for the red squares, we require that they're in an eigenstate of Z, 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 Z. So the X and Z Pauli operators anti-commute with each other. And to have a common eigenstate, you need that these things commute. But they do commute because whenever we look at two different checks, about, say, the X and the Z type, they're either completely not overlapping, or they overlap in exactly an even number of locations, 2 locations. And this means that even though individually X and Z anti-commute, together XX and ZZ commute with each other. And so they can indeed be a +1 eigenstate, a common eigenstate of these checks. And the gray qubits here are there so that they can help us measure these operators, which you can do by just preparing this auxiliary qubit in a superposition state, performing a series of, say, C0 gates, and then measuring the qubit out to obtain the eigenvalue. So what happens when we have an error in the system? If we have a bit flip that affects, say, the middle qubit, then what we see is that there will be a change in eigenvalue of all of the checks, or what we call stabilizers, that anti-commute with that error. And so if we have a single X error here, we find that this set of Z checks here and here will change in eigenvalue. And I'll always represent this by just making the gray balls larger. Okay, that's what happens if we have a single X error. But if we have a pair of X errors, what we observe is that we'll see a pair of these eigenvalue changes, which we'll sometimes call defects, at the ends of this string. So in the middle of the string, we see that this eigenvalue now actually is not changed. And the reason for that is that this string of errors has an even number of locations where it overlaps with the Z check here. So that's what happens when we have errors, but actually we don't get to directly observe errors. What we see instead are these changes in eigenvalues, and we know something about the underlying mechanisms that can give rise to these changes in eigenvalues, which we represent here by a graph underneath. And so this leads us to what we call the decoding problem, which is the part of the puzzle that Riverlane really focuses on, which is saying, hey, we've seen these changes in eigenvalues, and now we're going to try and solve this inference problem to figure out what the most likely error is that led to this observation. And that will correspond to finding the shortest path between these 2 points. Yeah, so sometimes when you have 2 paths that are kind of equal in length, they're often equivalent. So that's a very simple one there. But if we go to a much, much larger graph with lots more of these defects, we can now imagine that actually it's quite hard to solve this problem. And you need to solve it at very, very rapid pace to keep up with lots of qubits. So what we call megahertz speeds, at least for superconducting qubits. So it's a massive complex inference problem, but it's even more complex than just the simple picture I've gave you in 2D. Really, it's a 3D graph problem that you need to solve in order to perform quantum error correction. And so here, the qubit errors that I've already introduced correspond to horizontal edges on a single time slice. But other things can and do go wrong in qubits. So for example, our measurement could just give the wrong value. And so when this happens, we can think about it actually as a vertical edge corresponding to a pair of defects in the time direction. But there are other interesting things that can happen, like so-called hook errors, that give these kind of diagonal edges that run diagonally, having a bit of a flavor of both a qubit error and a measurement error. And what these correspond to are errors that happen in the middle of the circuit that is executed to measure these observables. Okay, so there's a big thing to do to kind of stabilize this many qubits and solve this complex decoding problem. So why do we do it? Well, I said that it gives you a more reliable qubit, but the scaling in terms of how quickly you can suppress errors is exponential. So actually, as you scale up quantum error correction by increasing the number of physical qubits per logical qubit, going to these bigger graphs as well, we find that the probability of an error per quantum operation is going to be suppressed from, say, what you have with the best physical qubits you can get today, which are around error rates of 1 in 1,000, down to any desired level. And so we probably want to get to at least 1 in a million, so you can perform computations that have millions of quantum operations. But many of the algorithms that people believe will deliver quantum utility require around a trillion quantum operations. So if you were using the surface code here, you would need about 1,000 physical qubits per logical qubit to achieve that logical error rate. So I'm going to walk you through now some of the exciting demonstrations that have happened in recent years, because quantum error correction arose as a theoretical idea in the 90s, but really what's been happening in the last couple of years are some really compelling and exciting demonstrations that quantum error correction is real and here today. So the first one I've chosen is this experiment from ETH Zurich, from Wallraff's group. And so they performed what's called a distance 3, a 3x3 surface code error correction experiment, showing that they could repeatedly stabilize the logical qubit over many, many rounds of QEC. So here they're going up to 16 rounds. So this was one of the first really compelling demonstrations that error correction is possible. It didn't quite kind of achieve the logical fidelity that they wanted, though, because if we look here in this plot, we've got the green dots that represent up here, well, the green and blue, sorry, represent different experiments they run preparing either the 0 or the plus logical state. But you can compare it against this dashed dot line down here, which represents the physical 2-qubit gate error rate. So what we see is that the logical qubit actually has a higher error rate than the physical qubit, although only slightly worse. The interesting thing here in this inset is showing that they have this notion of an improvement factor, which is based on simulations that show that they understand the noise reasonably well. And if they had improved the physical error rate by about a factor 2, they would have crossed this point here where the logical qubit would have become better than the physical qubit. So they were quite close in terms of the required underlying quality of the physical qubits. They were quite close to being what we call below the error correction threshold. Then the next experiment I want to describe to you is this one that came from Google. So again, the hallmark signature of quantum error correction is that as you go to use more physical qubits per logical qubit, you should see that the logical qubit gets better. And indeed, that's what they observed for the first time in this experiment, going from 3x3 to a 5x5. So here the red dots are the distance 3, the smaller surface code patch, and the blue data points represent the larger surface code patch. And you do indeed observe in this experiment that the logical qubit gets slightly better as we increase the size of the patch. So this is evidence that we're quite close to the error correction threshold here. The Google team were quite cautious. They never at any point claimed that they were definitely below the error correction thresholds, just that they were close to it. They saved that claim to very recently, and I'll come back to the more recent work in a moment. But I wanted to highlight that actually there are lots of different qubit types that have been demonstrating error correction. Here I'm just going to highlight some fantastic work from Harvard, where they showed that neutral atoms can be used to demonstrate quantum error correction as well. There are ways in which these experiments exceeded what the Google and Wallraff groups had achieved, and other ways in which they didn't achieve quite as much. So one of the things that was different is that they didn't do repeated rounds of error correction in this experiment. It was usually just one round of error correction, but they were able to move their qubits around in such a way that they could realize a much larger and kind of broader variety of approaches to error correction. And they, in fact, demonstrated 48 logical qubits in this experiment. So really a sign that error correction has arrived. So I promised that I would come back to the Google team. And so they very recently, only a few weeks ago, in fact, followed up with another experiment where they went from a 3x3 to a 5x5 and then a 7x7 surface code patch. And so not only have they gone to a larger surface code patch, but also they'd improved their fabrication and lots of other factors that fed into the quality of their physical qubits. And now what they see is a much, much clearer signature that they are clearly well below what we call the error correction threshold. So in this plot here that I pulled from the Google paper, you can see that the black dots are the old data from the previous experiments where the error rates are much higher. And then we see here the red dots correspond to the smallest 3x3 surface code. Then as they go up to 5x5, we get the kind of teal plots here that are clearly a lower logical error rate. And then we get to the dark blue, the 7x7 patch, where it's even lower again. And in fact, every time they increment the size of the surface code patch, they see that they get a suppression of a factor of more than 2 in the logical error rate. So really, we can see now that we can suppress logical errors potentially arbitrarily low, although really we need to kind of improve this factor, which they call lambda. I want to maybe just pause here for a moment and make a comment about metrics and how we should measure the progress in quantum computing. And I think this error suppression rate is a very good candidate for what we should be using as a metric to benchmark quantum computers. If you use some other metric like the 2-qubit gate fidelity or the 1-qubit gate fidelity or the measurement fidelity, these are all individual metrics that are going to be kind of varying greatly between different qubit platforms. But what you really want is to boil everything down to one single number that tells you how good your quantum computer is and somehow combines all of those composite metrics. And I think the rate at which you suppress errors as you increase the size of an error correction code is a really good candidate metric that people should be tracking. So in this short presentation, didn't have time to tell you about all of the wonderful different experiments that have been going on, but hopefully you got a bit of a flavor that there's been a lot that has happened in the last 2 years as we've gone from really being close to breaking even in terms of the quality of the logical qubit to seeing some clear demonstrations that we are well below the error correction threshold and able to scale up. So now I'm going to hand over to Jeremy so he can tell you how Alice and Bob are approaching this problem.
So thank you, Earl. I'm going to just get Jeremy into and get their slides.
Can you see my slides? David?
Yeah, now they are seeing your slides.
Okay, awesome. Thanks a lot, David. So first of all, thank you, David, for the opportunity to participate to this webinar, and thank you, Earl, for sharing this webinar with me and with Alice and Bob. So let me start my make sure I keep some time for Earl. So in this talk, I will give you a walkthrough the Alice and Bob architecture and try to give you a high-level understanding of why are we building fault-tolerant processor using cat qubits. So let me start where Earl stopped. So we've had just had a very nice introduction into the surface code. So what Earl was showing us is that by building a 2D array of qubits, you can, in principle, if you operate the surface code below its threshold, get access to arbitrarily low logical error rate. So here on this famous graph, you have the logical error rate of the surface code as a function of the physical error rate. And you see that once you're below a finite value, the threshold, then the logical error rate decreases as you increase the code distance, which is just proportional to the number of qubits you put into the array. And as Earl was mentioning, if you operate below the surface code threshold, so here as a x-axis, you have the again, the quality of the hardware, the physical error probability rescaled by the threshold. So here you're below threshold. Then you see that you can typically, the number of qubits you need to have a very good logical qubits is typically of the order of a few hundred to a few thousand qubits. More precisely, the experiments that Earl was referring to, so the experiment by Google in 2022 is right here, so at threshold with distance 5, and the one that was put on the archive just a few weeks ago is right here, so distance 7 with about 100 physical qubits and operated at a factor 2 below the threshold. Where we really want to be is really in this regime. So as Earl mentioned, for many algorithmic relevant error rates, you need to be in this region between 10 to the minus 10 and 10 to the minus 20, which means you have a typical overhead of about 1,000 physical qubits per logical qubit. Now, the goal of Alice and Bob architecture and cat qubits is really to decrease that number. So to perform error correction in a hardware efficient manner, meaning that we aim by using different qubits, we aim to reach those kind of logical error rates for a much lower physical qubit number. So to spoil the end of the talk, for instance, the architecture we have in mind, at least in theory, should be able to decrease this red curve here, where you target a logical error rate of 10 to the minus 8, let's say, which would require something like 300 physical qubits when you're 1 order of magnitude below threshold, down to using only 7 cat qubits per logical qubit. So the point would be right here. So this is a theory, and I'll now try to explain how this works in practice. So let me walk you through the CAD architecture, first in theory, and then I'll flash some recent experimental results so you can have a taste of where we are into developing that architecture. So to begin with, first, it's important to understand what is a CAD qubit, and it belongs to the family of bosonic qubits, which is different from a regular transpond qubit in the following way. So for a transpond qubit, you would build a harmonic oscillator, which you make nonlinear by replacing the inductance by the Josephson junction, a nonlinear element. And because of that nonlinearity, the energy levels of the Hamiltonian of that circuit becomes non-evenly spaced, such that you can selectively address the 0-1 computational subspace, meaning that if you apply a drive at the exact frequency to drive this transition, then you can selectively manipulate a quantum bit of information and code it into the subspace. And all of the other levels become useless, and they actually become bad in the sense that if your system escapes to those levels, then you lose the qubit, and this is known as leakage, and you have to fight against that. Now, for bosonic qubit, the paradigm is completely different. You really work with a harmonic oscillator, so with a linear inductance, such that you cannot encode the quantum bit of information into the 0-1 subspace, because now if you try to address the qubit by driving at this exact frequency, then the system will go to all of those levels. It will drive all of those transitions at the same time. So the paradigm of bosonic qubits is to encode one bit of information into this infinite dimensional Hilbert space. And there are typically two criteria which gives a good bosonic qubits. First, the two-dimensional subspace that you pick should have an interesting quantum error correction properties. So basically, you're looking for a subspace that has better properties than the 0-1 subspace. And second, you should be able to stabilize that subspace in the laboratory, meaning you need to be able to build something in the lab, a physical error mechanism that forces the state of the oscillator to remain into that two-dimensional subspace that you've chosen. Otherwise, you cannot encode a single bit of quantum information. So right now, there are two main contenders in the industry that meets both those criteria. There is the GKP qubit, which has nice property from a QSE perspective, which is that it minimizes the noise in a certain sense. But this encoding is hard to stabilize. And for instance, you can see that it's hard to stabilize because it took 18 years between the theoretical proposals in 2001 by Gottesman, Kitaev, and Preskill to use that encoding, and the actual realization in the lab of Jonathan Thome using trapped ions in 2019. The other proposal, which is sufficiently mature so that there are companies trying to industrialize that technology, is CAD qubit. So here, the CAD qubit encoding is rather easy to stabilize in the sense that the physical mechanism that you need to implement in the lab to stabilize a CAD qubit is now becoming quite mature. And the interesting quantum error correction property that you have with this qubit is that it polarizes the noise. So I'll come back to this in a moment. The price you pay for that qubit is that manipulating the information into a CAD qubit is harder, meaning doing operations on this qubit is not so straightforward, not as easy as it would for transpond qubits, for instance. So what do I mean by interesting QSE properties with the CAD qubit? By the fact that it polarizes the noise, is that if you apply a quantum error correcting code, just like Earl Campbell was showing the surface code, you discretize quantum errors, and you're left with two types of errors to correct. A bit flip error, which will flip the state of a qubit alpha 0 plus beta 1 into alpha 1 plus beta 0, so switching flipping the 0-1 value of the qubit, and the phase flip, which flips the phase of the superposition. Now, for many qubits, such as the transpond qubits, the timescales at which those two errors happen are typically of the same order of magnitude, let's say a few hundred microseconds, such that you have to correct for both errors at the same time. For CAD qubits, the fact that we use a CAD qubit polarizes the noise in the sense that we can have as much as 7 orders of magnitude difference between the rates at which those two errors happen. And so this comes from experimental figures that was published in Nature by Alice and Bob employees, and in collaboration with ENS Paris and a group of Sekilectas. So how do we reach such an important noise bias and long bit flip times? So the intuition is the following. Now I'm representing the Wigner function of a CAD qubit, The Wigner function is a function of the complex plane, which allows to represent in an abstract way the state of the quantum harmonic oscillator. And what's important to know is that the 0 and 1 state of a cat qubit are coherent state, which are Gaussians in this phase space picture. And the other important thing to know is that if you look at the typical error mechanisms that we have in the laboratory, such as a single photon loss or excitations, they would act as, in this picture, they act as local diffusion operator. So now if we increase the separation in phase space between those two states, which we can do by increasing the average photon number of a cat qubit, the probability that you have a jump from the 0 to 1 state is exponentially suppressed with the distance between those two states. Now, the price we pay to get, so that's how we get such a long bit flips. The price we pay is that if you look at coherent superposition of those two states, you see those fringes appear, which are typical features of the fact that it's a true quantum superposition. And now the other type of error, the phase flip, is just a shift of half a period of those fringes. Now, as you increase the average photon number in the cat qubit, those fringes get thinner and thinner. So if you have local diffusion in phase space on the vertical axis, then the probability that you have a jump, a phase flip, increases linearly with the average photon. It increases with the average photon number, but it turns out it increases only linearly. And so that's how, with only a few photon number, we managed to get 7 orders of magnitude difference between phase flips and bit flips. So I like to illustrate how this is hardware efficient by taking an example of a repetition code. So assume you start with a qubit that has no noise bias. So equal probability for bit flips and phase flips, and you embed that into a repetition code against bit flips. So meaning the logical 0 would be a tensor product of all zeros and 1 of all 1. Now, if you operate this code below its threshold and you look at the probability that you have a logical bit flips on this code, it decreases exponentially with the code distance, which is the number of qubits you put in the chain, because you would need to have a majority of those qubits to flip to have a logical bit flip. Now, on the other hand, if you look at the probability to have a logical phase flip, it's just it would happen if any of the physical qubits has a physical phase flip. And so as you increase the number of qubits in the chain, it increases linearly with the number of qubits. So it's somewhat analogous to the scaling you have with a cat qubit, but on one hand, you have a single physical system for which the role of the code distance is played by the average photon number. So to increase that distance, you only need to increase the amplitude of a microwave drive in the lab, meaning the experimentalist is just turning a button, but the chip is the same, the hardware is the same. Whereas on the other hand here, you have to rescale the number of qubits you put in a chip. So this is, in this sense, that a cat qubit is a hardware efficient quantum error correcting code. So now, this was all theory. Now I want to walk you through recent results. And so this exponential suppression of bit flips has been demonstrated in the lab, first in 2020 by Raphaël Lescan at ENS Paris. So here you have the bit flip time as a function of photon number in log scale. So this straight line means that it's you have an exponential suppression of bit flips. And here you have the phase flip rate in linear scale versus the average photon number. And so this straight line means you have a linear increase in phase flip. Now, in theory, you know, as you increase the distance in phase space between the two states, you should have an exponential suppression forever. Here, experimentally, we've observed a saturation at around the rate of 1 millisecond. And what it taught us is that at this rate of 1 millisecond, there is a physical error mechanism in the lab that induces non-local jumps in phase space of the cat qubits, thereby saturating the bit flip rate at 1 millisecond. This is exactly analogous to what you have in a regular surface code where, so here is a figure taken from the repetition code experiment by Google about 1 year ago. And so they operated the repetition code below its threshold, so they were able to witness this exponential suppression of bit flips as they increased the code distance up until a point where it's saturated. And here, this saturation indicated that there was a physical error mechanism that was causing errors on all of the qubits at the same time, which is, you know, when you make a surface code, the hypothesis is really that errors should be independent. This is really where this exponential suppression comes from. And so it's exactly the same kind of thing we observed with cat qubit, but now in this abstract Wigner representation. So in this experiment, it was understood that the saturation at 1 millisecond was caused by the the tomography apparatus used to measure the Wigner function of the cat qubit. So here is a schematic of the experiment where we have a cat qubit in this memory resonator. And here we use this auxiliary system to measure the state of the cat qubit. And it was understood that when the transpond had some errors, because it was coupled to the cat qubit, it could induce some bit flips on the cat qubit. And if you do the math, then we realized that this would induce bit flip at a typical rate of 1 millisecond. So the next step was to remove the transpond to check, whether the theory, until what point a theory worked. The problem is that when you remove your tomography apparatus, you're not able anymore to tomography the state of the qubit. So it took a bit of time to invent a new non-invasive way of observing the bit flips. And so this was another experiment done about 2 years ago in Zaki Lekta's group at ENS, where the bit flips statistics were observed by directly looking at the fluorescence field of the memory. And what was seen in this experiment is now, so again, an exponential suppression of bit flips with respect to photon number, that this time worked all the way up to 2 minutes between lifetimes. And so what we've learned from that experiment is that in the circuit that is used to stabilize a cat qubit, there is no non-local error processes happening on this typical time scale. So now just to finish the story, so this way of observing bit flips is not a true quantum tomography of the state. So we could not observe quantum superposition with this experiment. So that was fixed last year. And so here is another experiment where there is no transpond for the tomography. So the tomography is performed in another non-invasive way, but this time where we can observe quantum coherences between the cats. And so this is how, by increasing the average photon number, we were able to observe a cat state with a quantum superposition, so a phase flip lifetime of about 500 nanoseconds for a bit flip lifetime of 15 seconds, so about 7 orders of magnitude longer. So now, once we have this extremely noise biased qubit, how do we build a fault-tolerant quantum computer? The first step is to have a fully protected qubit, and so this can be achieved by correcting for the phase flips. So here there are 2 different approaches. If you have a finite noise bias, you can then use a variant of a quantum error correcting code, just like the surface code, that is tailored to correct for a finite noise bias. So for instance, you have in the literature many examples of how you can tweak the surface code to handle much more phase flips than bit flips. On the other hand, the approach we pursue at Alice and Bob is to rely entirely on the separation in phase space between 0 and 1 to suppress completely the bit flips, or at least up until the levels that are algorithmically relevant. And then we concatenate cat qubits in code that correct for phase flips only. So the simplest code that you can use to do that is a simple repetition code against phase flip. And more recently, we've improved that architecture by concatenating cat qubits in less naive phase flip codes, so LDPC codes to correct for phase flips. So let me just here pause for a moment and advertise for a very nice experiment that was done by the AWS team, also working on cat qubits. And they've shown this very Monday that they were able to correct phase flips on cat qubits using a repetition code. So here we have the distance, the logical phase flip error rate of a distance 3 repetition code using cat qubits, and here of distance 5. And as you can see, for the different photon numbers considered here, distance 5 has a lower logical phase flip error probability than distance 3, meaning the code is operated below the phase flip threshold for this value of photon number. So very first, up until now, all of this was theory, and the very first experimental demonstration was done this week. So to conclude the story, so now that we have a logical qubit that is protected, how do we perform computation? So we have a scheme that shows that it's possible to perform a universal set of logical gates. So logical gate means at the level of the phase flip code on which we have cat qubits, using the toolbox of physical gates that we know how to perform on cat qubits. The subtlety here is that all of the gates that you apply at the physical level on the cat qubit should preserve the noise bias, in the sense that I've argued how you can have a macroscopic bit flip lifetime in a single cat, but when you apply physical gates on a cat qubit, it's very important that you maintain this noise bias. So this rules out the possibility of having a universal set of gates at the physical level, for instance, because if it were universal, you could have a Hadamard, which would depolarize the noise. So fortunately, there is a set of gates that in theory, we know how to perform that preserve this noise bias, and those gates are sufficient in theory to perform universal computation at the level of the logical qubit. So now in the last few minutes I want to flash recent theoretical results we have on concatenating cat qubits into LDPC codes to have a very low overhead. So the construction is described in this paper we put on the archive earlier this year, and the figures, I mean the numbers are summarized in this table. So let's assume you would like to build a 100 logical qubit processor, starting from a physical error rate of 10 to the minus 3 with a logical error rate of 10 to the minus 8. So this figure of physical noise of 10 to the minus 3 translates in terms of cat qubit to a ratio kappa 1 over kappa 2 of 10 to the minus 4. So this is typically a metric for cat qubits that quantifies exactly the noise in all of the physical operations we have. If you were using a surface code with traditional qubits, then to suppress the error from a physical error of 10 to the minus 3 to a logical error of 10 to the minus 8, you would have to use a distance 13 surface code. So that's a 13 by 13 patch, so 169 physical qubit per logical qubit. And if you add the NCLAS, it's the 300 physical qubits I was mentioning in the introduction. Now, if you want to have 100 logical qubits, then you would need a total number N of 33,000 physical qubits. It's been shown recently how by using higher rate codes, the quantum LDPC codes, you could decrease that number by a factor 14. So this is a very nice recent work by IBM, and then code 100 logical qubit at this logical error rate using only 2,000 physical qubits. Now, this is kind of a similar overhead that we have with cat qubits concatenated in regular chain codes. So where for the same assumptions, you would need about 2,000 physical qubits. And when you combine cat qubits into phase flips LDPC code, this number gets as low as 758 cat qubits, including the NCLAS, for 100 logical qubits. So typically, this is a reduction of a factor 44 over what you would have with the regular surface code, and the numbers I was flashing. Okay, so I think I'm about done. I'd like just to comment on the assumptions behind these numbers, because they are always assumptions, and where we are now experimentally. So the processor would look like this. So we can build such a processor in a flip chip architecture with a chip that would have dimensions somewhat similar to chips that IBM is already building, for instance, such as the Osprey chips. And the theoretical targets would need, the numbers we need to obtain such a low overhead is kappa 1 over kappa 2 of 10 to the minus 4, where today we are routinely below 1%. So in the first experiment, this number was of about 2 orders of magnitude, a bit more than 2 orders of magnitude have been gained just by circuit engineering. And now we're still working on improving this number and think it's reasonable to get to 10 to the minus 4. The bit flip lifetime of a single cat qubit needs to be of about 13 minutes to get this overhead. So right now, in what's been published, the number is about 15 seconds, but we know routinely how to achieve a bit flip lifetimes above a couple of minutes. And so, for instance, there is a cat qubit in Alice and Bob cloud that has such a number. And the real, I mean, the last ingredient that's missing and on which we are working at the moment is really to demonstrate an entangling gate between cat qubit that preserve this macroscopic bit flip lifetime. And so this is a work in progress at this step. So I think I'll stop here. I'll hand over to Earl, and I'll be happy to take questions at the end if they are.
Thank you, Jeremy. The things you show looks amazing, actually. So as Jeremy said, feel free to post questions on the chat. They will be answered at the end. And I would like to jump in with Earl again.
Hello, I'm back. Let me share my slides again.
Sure.
Okay, you good?
Yeah, they are not in presentation mode, so
Okay, here we go.
perfect. We'll let you for the end.
Okay, so we've had a bit of an overview of what quantum error correction is and seen that there's been some really exciting experimental demonstrations recently. And in this last part of the talk, I'm going to quickly blast through what Riverlane's contributions are. So as I mentioned, we don't build our own qubits. We work with partners like Alice and Bob, and then we provide the classical electronics that goes alongside the qubits in order to solve the data processing problems and figure out how to kind of control and implement quantum error correction. So this is our company roadmap that you can read more about on our website. So we call our product Delta Flow, and we're going through successive versions of it. We've already built the first generation that we say solves the backlog problem, so we can stabilize a large surface code patch and decode at very rapid speeds, fast enough to keep up with superconducting qubits. Later this year, we'll be releasing a version that does things in true real time, streaming real time, and also handles other types of noise like the leakage errors that Jeremy was talking about. And we're also developing what we call a universal interface, so a kind of common standard that anyone can build their control system to work with our QEC stack or even indeed anyone else's solution. And then the successive versions are going to build more and more features in terms of supporting error correction whilst performing logical operations. And we're building up towards a system that would support, say, of the order 10,000 physical qubits, doing up to 1 million operations. So this is going to be a big pivotal turning point in the field when we reach this, because we'll kind of pass this threshold where we think that conventional computers will be able to simulate such a quantum computer, but still there's more challenges to scale up to what we call the gigaquarp and teraquarp scale. So all qubits are different, and so we really need to customize to some extent the QEC stack for different qubit types. And so what we do is we kind of divide it up into 3 different tracks. So we think about systems that are, say, strictly fixed in 2D, say using lattice surgery for performing logical operations, like you would do with the surface code. Track 2, where you can still use the surface code, but you have, let's say, reconfigurability that allows you to do logic using transversal gates instead. And then a 3rd track, which is based on generic decoding of LDPC or QLDPC codes, such as the type that Jeremy was commenting on. Okay, so in the first part of my presentation, I pointed out that actually the decoding problem is a very, very large, complex decoding problem on graphs. At least that's how it is for the surface code. And what we believe at Riverlane is the only way to keep up with the qubits at solving this kind of complex decoding problem is to build dedicated hardware. So we build dedicated chips that solve this problem at rapid speeds. I like to have this slide that kind of makes it a little bit more real what I mean by building hardware. So actually, we're not a foundry or a fabrication facility. We send our designs off somewhere else to be fabricated, but we also use FPGAs. So mostly what people do is they work in a language, a hardware description language, such as System Verilog, that can then be taken down to a field programmable gate array. This is how we do most of our day-to-day work, because field FPGAs are reconfigurable. So that means that we can just change our code, and then we get a bespoke piece of hardware that kind of solves that specific task really well. But FPGAs are bigger and they have slower clock speeds than if we actually fabricated a set of transistors which solves specifically that problem and only that problem. So long term, this is the way to go, because ASICs are smaller, they're faster, and they're lower power compared to FPGAs. But once we have fabricated them, the logic is fixed. And so if we want to innovate quickly, we really need to be working with FPGAs because they can be reconfigured much more rapidly. So we mostly do demonstrations with our partners using FPGAs at the moment, but we do all of our System Verilog work in such a way that at some later time we can deploy it as an ASIC. And here are just some metrics that came out in a paper that is on the archive last year and due to be published very soon. And so what we have here are some of the metrics that we got for our ASIC, and we found that we could, if we taped it out using something called a 12 nanometer FinFET process, it would take less than a millionth of a second to decode all the way up to a code distance which can handle, say, the teraquarp scale algorithms. So suppressing error rates down to 1 part in a trillion. And this chip design is very low power. It uses less power than a smartwatch. in sleep mode. The die, so excluding kind of all of the I/O parts of the chip, would be smaller than the cross section of a grain of rice. And I actually don't have an image of the actual chip taped out. For this particular generation of the hardware, what we have instead is a floor plan, which is literally a map of where all of the transistors and wires between those transistors go. So we have some exciting results that should be on the archive in the next couple of weeks. And so this is work that we've been doing with Rigetti, where we have delivered Riverlane's real-time decoder onto their control system and demonstrated a real-time error correction experiment with extremely low latency for the very, very first time. So this is figure 1 from the paper that actually details all of the different contributions to the latency in their device. And it's the first time that someone's done an error correction experiment in real time, where we've measured the time it takes to decode, but also all of the other contributions to decoding, including control system logic and readout propagation, for a decoder that is inherently scalable. So there have been some demonstrations that have used what's called lookup tables that don't scale well. So this is an algorithmic decoder that will scale all the way up to thousands of physical qubits. And so with that, I'd like to thank you all for listening and take questions.
Thank you so much, Earl. The things that you show look amazing, actually. And thank you for sharing this. I don't know how official it is, this information. So I'm gonna start with the Q&A. And I have seen that there is in the chat, there has been some questions. So I'm gonna get them so we can show it. So Jeremy, could you explain again why a bias preserving gate set cannot be universal? This is asked by Gianluca Spritzer.
Yeah, so I made the argument very quickly. Let me explain it again in a bit more detail. So if you have a universal set of gate at the physical level, then it contains gate that will necessarily depolarize the noise, such as the Hadamard gate. So this is why it cannot be universal. Because you know, when you apply a Hadamard gate to a physical qubit, it has two effects. First, it applies a Hadamard gate to the encoded bit of quantum information, which is exactly what you're looking for. But also the Hadamard gate is applied to whatever noise you have on the physical qubit. So if just before the gate you had a lot of dephasing noise on that qubit, then after the gate, you have a lot of bit flip noise on the physical qubit. And so if that qubit is concatenated into a code that cannot correct for bit flips or can only handle very few bit flips, then you're ruining the fault tolerance. And so as for the references, so David have given 2 papers in the chat, which one of which is ours, and there is also the a different construction of logical gates from the AWS team. Actually, it's Earl that is doing this one. So.
Yeah, for AWS, I also worked on cat qubits for a while. No.
I have just posted them in the chat. So
yeah, maybe to add to what Jeremy said about universal gate sets, it's actually quite remarkable that you can build a universal set of operations whilst preserving the bias. But the trick, of course, is that you use teleportation. So it's not just gates. There's also other gadgets in there that help you get universality. So you can get universality. It's just, it's not purely by gates.
So for now, I don't see more questions while they think about their questions and maybe ask them. I have a question for Jeremy, actually. You have been talking about, for both, but you have been talking about the cat qubits and the cat architectures. Could you elaborate on the challenge of implementing this architecture and how Alice and Bob is addressing this problem? Or you can jump in if you want, because you have also worked with this.
I would say at the theoretical level, so those are more recent qubits that were really proposed with error correction in mind. So really the point I was making about bosonic qubits is really you're trying to leverage that infinite dimensional Hilbert space to get some of the redundancy you need for error correction without blowing up the number of physical systems you have to build on the chip. So cat qubits are one of those. Now the difficulty into building those is that it's not just the 0-1 subspace of a physical system, which is like a more natural way of encoding a bit of information, I mean, which requires technologically less advanced methods. Here for cat qubits and for other bosonic qubits, you really need to engineer that stabilization that forces the state of the oscillator to remain into that two-dimensional subspace. So just the fact of building an idling qubit is already involves some kind of active mechanism that you have to build in the lab. And then performing operations between those qubits is also more involved. So I didn't get into the physics of how you can perform gates on cat qubits, but basically it involves pieces of technology such as driving parametrically nonlinear systems. So, and it's a kind of physics that is more difficult to master in a very precise way. It requires a level of Hamiltonian engineering that is not yet state of the art. So a big part of what Alice and Bob has been doing in the past couple of years, and also other competitors betting on those bosonic qubits, is really to push the boundaries of how good we can master those systems, to really engineer the Hamiltonians we need for the interaction between those qubits and nothing else. Don't know if it makes sense, David.
Yeah, actually, it makes a lot of sense. So, as there is no more questions in the chat, I will go for Earl again, and I have a question for him. We have seen that there's had been a lot of advancement in quantum error corrections, but what do you think of, what do you see as the most critical next step in reducing the gaps between the physical and the logical qubits?
Yeah, so I think we have seen a lot of progress, but one of the things I highlighted was this kind of key metric, which gets called lambda sometimes, which is the rate at which you suppress errors going from as you increment the size of the surface code patch. So Google saw that it went down by more than a factor 2. And to get any kind of practical overhead for the surface code, this needs to be at least 8 or 10. And so the qubits have come a long way, but they've got to get us a bit further, unfortunately. And not only do they have to get us a bit further, but they have to do it at scale. So you could imagine that you scale up one of these devices, and if you assume that all of the physical error rates are the same, that's, you can predict what kind of performance you're going to get. But unfortunately, especially for superconducting devices, you have fabrication and yield issues. So the chance of building a massive monolithic chip that has, say, 10,000 physical qubits that are all high fidelity is very unlikely. And so there's a lot of work has to be done to, say, modularize these chips into chiplets and then combine them together so that you can tolerate finite fabrication yields.
Well, that makes really sense, and that gets to my last question, I guess, for both. As we QuIC are pushing in the European landscape, and we have seen that Europe has seen significantly progress in the quantum computing, like projects are companies like yours. I want to ask you both, what do you think that, maybe it's a spicy question, what do you think that are the key collaborations or partnerships that you believe that are necessary to push the fault-tolerant quantum computing forward in the European landscape? As you were saying right now that there is maybe problem about making the chips. So what do you think, both?
You go first, Jeremy.
Yeah, I mean, I was just taking the opportunity, since fabrication issue, for instance, is really something where the European ecosystem has a role to play. We'd love to have large European foundries that allow us to reach the level of maturity that some of our American competitors, such as IBM, for instance, have. And this is agnostic of the type of superconducting qubits that we're using. We really need a good foundry. So this is one good example, for instance.
Errol, any thoughts?
Yeah, I think we just need to keep nurturing an open, collaborative culture and not get too siloed. It's definitely important for a company like Riverlane that we work with a lot of different partners.
Okay, thank you. So we have one last question, and then we will close this wonderful session. So here in the chat, Vincent says, how does Riverlane decoder compares against Yale open source decoder?
Yeah, it's a great question. So there was a decoder architecture, which they call Helios, that was released from a team at Yale, and it's very different from the metrics that I just showed you. So it's faster, but it's also very, very high power and uses a lot of FPGA space. So in that experiment that I described where we worked with Rigetti, essentially we had like an instance of our decoder sat on the control system, and it took, a few percent of all of the space on this FPGA. I think, though, as we move into the next generation of our QEC stack, we're actually moving towards something that's a more distributed algorithm that will also be faster in the same way that the Yale one. So I think it introduced some interesting ideas.
Thank you both. So we had get to the end of this wonderful session. So I want to extend my thank you to you both, fantastic speakers, Jeremy from Alice and Bob and Earl from Riverlane. Thank you for sharing your insights towards the fault-tolerant quantum computing and in general about these wonderful technologies. And I would also like to thank you all who joined to this first episode of our QWave webinar series. Thank you for your questions also. And this marks the beginning of the series. So stay tuned for the next topic that we will showcase with different speakers from different companies. And just last quick thoughts. And I'm gonna hide you for a little bit. This couldn't be done without QuIC. So QuIC is the European Quantum Industry Consortium. Be sure to follow us in LinkedIn, subscribe to our YouTube channel, follow us in our website. The QR code maybe is not visible. Anyways, I will share the links in the chat. And with this, we are closing. Thank you again, Earl. Thank you, Jeremy. And thank you all.